Record it. Okay. All right. So where were we? Okay. We were talking about now it turns out that if you know anything about how um, something oscillates, if they oscillate with a simple harmonic motion. Now, what is meant by simple harmonic motion? Now, what I'm going to do, hold on a minute. So what I'm going to do is I'm going to attempt to bring up my and now what I'm going to do is we're going to have a look at my tablet. Okay. Slow. Okay. So you see that. Okay. Okay. Let's stop share because you still don't see anything. All right. And what I want to do is I want to show um, properties of waves. Okay. There we go. Now let's share what I see on the tablet. Okay. All right. Now the general idea here is that if something oscillates in a simple way where it goes, let's say it started out originally here and then it moved here and then here. So it changed its shape to there and then to there and then back to there, then back to this location and then back here, and then here, if you will, so to speak, a mirror image of what is that. Okay, and it went back and forth, vibrating back and forth. Now, this is called simple harmonic motion. Okay. You know, the example of the spring, of course, say if we had a spring hung from something fixed, and the spring is kind of like this, and it's hanging on to something. Could be a ball, could be, paper clip, something. And this thing is just going up and down and it's vibrating, it's changing position. So if it changes position with a motion that if we were to plot, in this case, y, so let's let that y equal 0, and it goes up to y here and then y down there, and it goes up and then down and then up and down And what we're plotting is its change in position and time. We would say that this thing would move up and down, sinusoidally. Okay. Now you recognize that as the root sinus, which is often meant from Latin for rhythmic. Okay. And the whole idea is that, perhaps you've heard maybe in a medical show, a doctor, whether doctors and nurses, and say, well, he's breathing sinus. He has sinus breathing, or we have in heart have sinus rhythm. So that means it's we're breathing rhythmically, and that what we have is a correct motion. But in this particular case, the word sine, or often just spelled sine, as in sine wave, is in mathematics the sine function. Now it turns out that things that change position, whether it's x or y, in this case the spring, will go up to a y max, and then sorry about that, a y min. Okay. So we would call this the amplitude. Let's spell the word out. Amplitude. Okay. A for amplitude is what we're going to use here. And we were to write out the function for it. It looks like A times omega t plus something. Okay. Now, this is the so-called frequency in radians per second. Okay. Rad per s. Okay. If we were to convert this to frequency, of course, f, the frequency of just the time, of repetition. How many times does it do this in one particular second? All we have to do is simply say whatever that is in 2 pi. So that means that omega is equal to 2 pi f. And of course, the timing of this thing will be 1 over 2 pi, 1 over this, or equal to no, sorry, it's equal to 2 pi omega. Sorry, let's erase that. Now, so it turns out that the things that go up, that change, we have you know, we have a definition, something that has simple harmonic motion will simply repeat itself. And if we were to somehow find a way to graph it in time, and if it changes its size, change its position, change its angle, I don't care what it is. And if that, whatever that is that happens to change, it changes rhythmically with a sine in the form of a sine wave. Okay? If it changes rhythmically, somehow where we say, that thing, whatever the function that it looks like in time, whatever it happens to look like, it looks like something with sine in it. Sine, the angular frequency, the amount of time, and this. This, by the way, is called a phase offset. And it's arbitrary. It says, hey, I'm going to just say, this is the beginning. Make that 0 or make that something 0 or something like this. Okay? By the way, sometimes this looks like this. And the reason is that you can convert from one to the other. Oops, that's what I'm going to do is change this and call this, let's call that, that, I don't know. I just made it simple, okay? I couldn't decide on the symbol, so I just wrote a squiggle down. But the whole idea is this, that sine and cosine are very related. And you've probably have seen that they look kind of like this, where this is a sine wave, been drawing it all along, and this is a cosine wave, where it turns out that they're 90 degrees separated. Going back to my notes, stop share. Where's the notes? All right. All right. So let's take a look at some examples of harmonic motion. And when we're done with the concepts of harmonic motion, we're going to then go on to a more complex harmonic motion. It turns out most things, in my personal opinion, do not exhibit harmonic motion. It seems like it, but they often don't. Okay, so let's have a look at, simple harmonic motion, say on a, we're setting this thing up to make it look like it's, that is not, trying to make it as simple as possible. Of course, it takes an awful lot of equipment to make this work, but that's what we're going to do. Okay, so let's take a look at this. I'm going to stop share and I'm going to look at, what do you call it again? Videos, well, 14, 16, so on and so forth. So let me stop the share. You'll see my face for a little bit while I bring up the particular disk or a set of videos. And let me set this thing up. Okay. Okay. Now what I need to do that, I need to begin to share again, to share that particular video. And I'm going to, you'll see, hear the sound and you're going to hear it. And it should be even better than you have ever seen it before in the lecture, because it's being recorded right off of my laptop here. Okay, here we go. All right.
We'll use this glider floating on a...
So as usual, what we have here is an air track. And on the air track, and the air track is nothing more than a piece of extruded aluminum, and it's hollow inside and air is blowing through. And at the edges here on this side, by the way, this is triangular, so you can't see the other face down on his side. There on the other face, there's also a set of holes, and out of those holes blows a jets of air, creating a cushion of air underneath this thing and allowing it to glide freely up and down the track.
Cushion of air and these springs to investigate simple harmonic motion. If a spring is attached to each end of a glider, the glider will oscillate back and forth on the track. What will happen to the period of oscillation if we double the mass of the glider?
So that is a question. What will happen if we increase the mass of the air car or glider, as they're calling it? There's no right, by the way, there's no right terminology here. Glider is fine, air track is fine. But he put on a bit of mass. I bet that mass is brass, but it doesn't make any difference. So it made it heavier. Now, if you kind of remember, for the pendulum, mass had a effect on the frequency. And if you remember, we even for springs, mass had an effect on its period. Well, would you think that it would be any different here? So let's find out what happens when he puts the mass on there. So
The
there it
top
is.
half of the screen shows the original arrangement, while the bottom half shows the glider with twice the mass. The period has increased.
Means it takes longer for it to go through its cycle.
What will happen to the period if we add another spring to each end of the glider instead of more mass? The top half of the screen now shows the original setup, while the bottom half shows the glider with another set of springs attached. The period has now decreased.
So if you remember for springs, if you have two springs with the same spring constant, and these things have the same spring constant, and if you combine them in parallel, it's as if you're adding the spring constants together.
To show the form of this type of motion, we will mark one point on the glider and use it to draw a graph of position versus time.
So there you go. This is it's a sinusoidal motion, and so it has a sinusoidal periodicity. Now we'll do the next video. Let's see, I gotta go look at my notes. 14 is what I want to do next. Okay, so let's have a look at pendulas. Okay, let me drag and drop thing because it's already shared properly.
These two pendula have the same length but different mass.
Oh, my bad.
How will
It's
their
not
periods
sharing
of
it properly.
oscillation
Let's do
compare?
it again. All right. Let's do it again. Stop. Start it again.
These two pendula have the same length but different mass. How will their periods of oscillation compare?
So they have different lengths, but different masses. Okay. Now, if we were to remember, so what do you think is going to happen? Do they have the same period? Do they have different periods? You know, are they going to be they have the same harmonic character? Same sinusoidal character.
Their periods are equal. Mass has no effect on the period of a pendulum.
By the way, just as a bit of a side, it turns out that the angle, the initial angle, or the total deflected angle, does have an effect on this period. Interesting enough. All right.
Here are 4 metal arcs.
Sorry about that. There's something wrong with this. Okay. We will stop share and then redo it.
Here are 4 metal arcs, each of which is an increasingly large portion of identical circles. Each arc has a hole at the top for a pin support on which it can swing like a pendulum. Which arc will have the longest period of oscillation?
Yeah. Which one?
All 4 arcs have equal periods.
And by the way, you would get the parameter for whatever the sign is, it's angle. The angle is changing at time, by the way, not X or Y. Oh, of course, X and Y is changing. All right. Now, next one coming up. We're going to do a physical pendulum.
This aluminum bar hangs from a bearing support.
Now, what I want to emphasize is the difference between a simple pendulum and a physical pendulum. In a simple pendulum, all the mass is considered compact and very compact down. Ideally, as a point, of course, no mass is really a point unless you want to do this to a black hole or something like that. But barring having a black hole available, you just use a ball of anything, okay? And so but in a physical pendulum, all the mass is distributed throughout the length of the string. In fact, the string becomes something that has mass. That isn't to say that strings on a simple pendulum don't have mass. They do. They just have it very tiny in comparison with if we were to make this entirely, say, piece of metal or a piece of wood or something of that nature. So this is going to be a physical pendulum.
So that it swings like a pendulum. If we compare the period of this physical pendulum with that of a conventional pendulum made of a string and mass, we see that the physical pendulum has a shorter period.
He's just trying to move it out of the way.
To match the period of the physical pendulum, we need a string pendulum that is 2/3 the length of the physical pendulum.
So yes, so that's the equivalent length of the physical pendulum compared to a point or simple pendulum. Okay, 20 to 23.
This rotating disc and a weight on a spring will be used to show the similarity between uniform circular motion and simple harmonic motion. A spot on the edge of the disc allows us to see the constant rotational speed of the disc. If we set the weight oscillating in time with the spot on the disc, the weight is always at the same horizontal level as the spot.
This rotating disc and this pendulum will be used to show the similarity between uniform circular motion and simple harmonic motion. A spot on the edge of the disc allows us to see the constant rotational speed. If we start the pendulum swinging just as the spot passes the pendulum stays in a vertical line with the spot.
And phase shift. Now, I don't know if you've ever noticed,
These
let me
two
tell you the story in a
spheres on
moment.
the edge of a disk rotate with the same period. We'll backlight the spheres so that their motion appears one-dimensional and simulates simple harmonic motion. We can change the relative phase of the spheres by moving them to different parts of the disk. Here the spheres are moving in phase. Here they are moving with a phase difference of 45 degrees. Here is a phase difference of 90 degrees. (135 degrees), (180 degrees).
All right. And now for non-simple harmonic motion.
The motion of this heavy pendulum bob can be described by a sinusoidal function of time. This special type of motion is known as simple harmonic motion. The motion of the flexible wire at the top cannot be described by a sine function. It is not simple harmonic motion.
In fact, it is called complex harmonic motion. And the reason is because, well, it has a periodic motion, a periodicity. It repeats its pattern over and over again, but it is not simple sinusoidal or cosinusoidal motion. It is complex harmonic motion. Now, that's a simple complex, a simple example of a complex harmonic motion. There's lots of things that are far more complex than that. But, so get what you will out of that. But the point is that it is a complex harmonic motion exists everywhere. It's very common. It is something that we often don't relate to. We often just think of. It's much easier to imagine and much easier to relate to simple harmonic motion. And it turns out that simple harmonic motion is pretty, what's the word for it? Boring. Okay. Now, the last thing I want to show you is pendulum waves. Let's get this up here, and why we're still saved here. And
15 independent simple pendula are suspended from a rigid frame. The lengths of the pendula have been carefully chosen so that the phase change per oscillation between any two adjacent pendula is the same. Notice that as they oscillate, they create a continuously changing pattern of traveling and standing waves.
so look at the waves. It looks like they were standing and now they're moving. So because as their phase change, and now they're returning very slowly back to their original position, and now they're repeating it. So stop that. Go back to the notes, okay? And let's discuss one. Now, I wanted to share with you a little bit of a, how should I say, it's hard to relate to it. Let's see if we can go back to the tablet, okay? Let's go to the tablet and let me draw it out. We're sharing the tablet here. Now, all right. Now, you may have been stuck in traffic at one time or other. And sometimes what you would see is that the car in front of you, and I'm just going to represent the car as a for a box. And then what I'm going to do is I'm going to draw a little, the turn signal light on it. Okay. So the turn signal light is on. Okay. And there may be another person's who's, let's move this over because what I want to do, I'm going to get rid of this turn signal. Let's get to this. Okay. So there are two cars and they're both turning left, let's say. Okay. And this is on, and then this one is on momentarily. And then what happens is that a next moment later, this is time equals 0, okay? And then sometime later, then what happens is you might see it that this is off, but this is on. And then you might see sometime later that this one is, let's do it this way. Hold on now. Let's do it this way. On, then on, and then on. I got to make sure they're about 3, 1, 2, 3, 4. Oh, that I missed it. I want it 4. 2, 3, 4. Here we go. 2, 3, 4. So which means that in time, and then here, it's blinking. So what this is time, okay? And then the other car, let's change colors for the other car just for the sake of argument. And so we can see, and this one starts out like this. It's on, and then it turns on here, and then it turns on slightly different time. You see, this is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Here we go. And then 1, 2, 3, and then 1, 2, 3, and then 1, 2, 3. So the whole idea is they blink at slightly different rates. Sometimes they look like that they're in they start out, they're blinking at the same time. And then sometimes they look like they're blinking at then a little bit later. It looks like this one blinks first and then this blinks second, and then looks like that they're completely out of sync, and then they come back into sync again. So there is this happens sometimes between when it's as if the phase is changing between them. So we would see kind of a phase. In reality, what's happening is that the blinkers on the different cars have slightly different frequencies, it turns out. Okay. right. Now, there is a thing about harmonic motion, and it's not hard to do. Harmonic motion turns out that most things don't continue to oscillate, go back and forth continuously without any new amounts of energy inside it. Okay? Now I'm going to turn off sharing because I want to show you something really quickly. What you see here is my phone, and on it is this long spring that I showed last week in the lecture. Now, if I hold on to this thing, I've set it in motion, and it's slowly slowing down. It's slowly oscillating less and less and less. Its oscillation is decaying. Of course, I'm holding it, and of course, this whole thing is a bit, how should I say, a bit of a fool's game. It's, here's started up again. I'm making it go with just my fingers. You can't see them. My fingers are off screen above. Now I'm going to try to do nothing. Slowly, it's losing its energy. Slowly, it's giving up its motion. Slowly, it's losing whatever potential energy it could have. And eventually, it will come to a rest. We say that this is exhibiting damped harmonic motion. This is the terminology for it here, damped harmonic motion. Damped harmonic motion means that, of course, eventually what happens is its motion, its characteristic as an oscillator, its characteristic as a harmonic instrument. Eventually, it's going to give up its energy to something else. In the case of my phone, I don't know what it was. Spring, absorb some of the energy, just moving, maybe air, whatnot. And, so the energy, of course, dissipates. And because of that, we say that its motion is damped. Okay. Now, damping turns out to be everywhere. An example, and I don't know if you know this. Let's see if we could find it real quick on a web search. Door damper. All right. Here's a good picture of this. I will share this now. Stop share. And then I'm going to reshare this. Okay. You may have seen something like this right here. Okay. And maybe you've seen it in another form. They sometimes, okay, how about car? You may have seen it here in this thing. Sometimes they're known as struts. In my previous car, which about a year ago, I replaced it before I sold it, so you can, get a better price on it. These things. So if you have a hatchback, you have one of these things in there, so it keeps the lid. It keeps the door from closing, slamming shut, and holds the door open, if you will. These things are often called dampers, and they dampen the motion. They're designed to absorb the energy out of a system, out of, in this case of a door. They do exist. Okay. Let's look it up. See, that's what it looks like. I'm sorry about that. I just want this. That's it. So, all right. It's called sometimes known as a gas spring. But anyways, you get the idea. And if you in the future will own a car, You will, of course, encounter them if you buy a hatchback. All right. Let's get rid of that. Let's go back to our notes. Now, motion that, many of these cases, they are designed to dampen the motion in such a way that we want them to be critically damped, meaning they take at the most time, they take exactly the time they need to, of course, return back to the original position. Now, critically damped, now this is beginning the end of the notes, okay? Now, critically damped comes about like this. Let me show you something. Critically damped harmonic motion. Critically damped harmonic. Doesn't make any difference, oscillator or motion, whatnot. What I'm looking for. So when the motion is damped, this is what happens. That's what we saw with the spring, with my phone at the end of the spring. Up and down, and eventually it came to a stop. Now, if I had critically damped it, that motion, say I started up at the top, released it, it would have done this. If it was too damped, it would just take a long time to return back to its original position. And in fact, may even never return back to its original position. If it's overdamped, means it got stuck. It's no energy that can overcome it. And so no motion that can overcome its position. So it just simply stops in place. This is what we, in the case of the doors, like the door dampers and so on, this is what we aim for usually, or at most maybe a little bit, a little bit less, but so we want the door to close completely, but we want to do it as smoothly as possible. Of course, we don't want the door to bounce back and forth. Makes sense. And of course, this is what we do not want this, for instance, underneath our car in our suspension system. We don't want the car to bounce up and down. We really want it to be as smooth as possible. We want it to be as critically damped as possible. Doesn't always occur. Many of you might have an older car in the family, and if you have an older car, you go over a bump a bit too fast, and you might go up and down, up and down a bit too much, because it's the shock absorber or the suspension struts or whatever they're called underneath, just can't absorb the energy as well as it used to. Okay, probably in a moment that I'm be told that I'll have to change to a. We'll start over the video. I'll start onto a next recording. Now, the thing that we want to go to next is we want to talk about resonance. Okay, what is resonance? At this point, if I were teaching this in class, I would be asking you, what is resonance? Many people have an understanding of what a resonance is somehow, where a resonance is so what I'm going to do. Oh, you know what? I never stopped. I never started to share that screen. Yeah. Somehow I never shared with you this. This is what I wanted to share. So let's do this. In which case, this is what motion would look. This is what the motion of, or I should say, this was the motion of what my phone did. Took a little bit longer, but this is the underdamped motion of my phone on the spring. This is what it would look like if it had gone back down to equilibrium, to the place where it's just hanging from the spring, but it did it in the least possible time. But this is what happened if it was too damped and couldn't return back to it. It's like this. Let's stop sharing. Here we go. Here's my phone. Okay. Hold on a minute. It's on. Something happened. It went into a puzzling mode. Thank you. Go away. All right. So here's my phone. Okay. Good. So if I had dampened it, there, I dampened it and it returned. But if I over damped it, like for instance, it's up here. Okay. Let's get rid of it. Ow. You know, if this stuff gets in your hair, it really hurts sometimes. Okay, there we go. It's bouncing back and forth. But what happens if I dampened it too much? Now, what would happen if I released it because it's damped too much? Well, actually, let's do this just right. Come on. If I did that, it would, if I released it, it couldn't because I had over damped it. It could not return back to my original position, its original position. All right. Now, we'll go back to what we're talking about. And now we're going to move on to resonance. So sorry about that. Now, resonance. Now, there's lots of examples of things with resonance. And of course, this is a recorder, by the way. I don't know how to play it. Wish I did. Once upon a time, I thought that I might learn it, but never found the time. So it's as you know, it's if you cover up all the holes, it makes a certain sound of a certain type of note, and of course, uncovering the different holes in a different order would allow me to go from one note to the next. Okay, and of course, resonance means pardon me. Resonance, has a meaning that where we often get that something produces the same sound over and over again. Another example, consider this bell. Okay. Got this bell. I found this, by the way, in a trash dump 30 years ago. Interesting. I just found it. I don't know what it was for, but I think it was used for school. Once a time you go, okay, all right, go back to class. So this thing is also an example of a resonance. It makes a sound, and it makes the same sound pretty much every time that I stroke it in the same way. But what is resonance really? Now, by the way, I looked up what resonance is on a couple of different places. So I asked, for example, ChatGPT. So let's have a look at ChatGPT's answers to that. Okay, I'm going to switch over to a browser. Share browser. Okay, good. All right. Now let's go to Chat GPT. What is resonance? I misspelled it. I should have put an X. Resonance is a physical phenomenon that occurs when an object or system vibrates its natural frequency. By the way, so hold on a minute. And then let's look at Gemini. Okay, and ask the same question. What is resonance? Okay, resonance is a phenomenon that occurs that when an object or system is subjugated to an external force or vibration, all right, that matches its natural frequency. And then let's ask Copilot. All right. I don't. Let me answer my question. Forget this. What is resonance? With the question mark this time. Hold on. Oh, I think some resonance. Okay, let's call this meadow.
Let's explore.
Okay, I don't care to do that. What is resonance? Okay, resonance occurs when an object or system is driven to oscillate at its natural frequency. They all mention, here's the keyword here, natural frequency. Natural frequency. Natural frequency. Okay. There's a problem with that, it turns out. It's not exactly. It turns out these definitions are not entirely correct. Okay. There is a good reason. So, it's unfortunate that they are the same answers. Okay. Now, let's ask the question this way. What is resonance? Just using the normal Google now, two things I want to point out. Wikipedia, okay, which we'll see in a moment. And actually, interesting enough, when I did this earlier, there was Britannica's answer. Beyond, it turns out that Britannica is much, much better vetted and written in the original version of this thing than Wikipedia. So here is Wikipedia's answer. Okay, or whoever wrote for Wikipedia. Remember, Wikipedia is not a writer. It's just of course, a recorder for whoever had written the information. So whoever the semi-anonymous author is. Okay, so it's a phenomenon that occurs when an object or system is subject to an external force. We saw that, and that matches this natural frequency. But interesting enough, Britannica, it turns out I trust Britannica a little bit more in this regard. Britannica has a long history of asking experts, professors, people who work in the to teach or have deep knowledge of this stuff. They'll invite them to write various entries in their encyclopedia. These people may be dead by now, but the whole idea is what they wrote still stands. So resonance and frequency is a relatively large selective response of an object. Wow, unpack that one. Of an object or system that vibrates in step or phase with an externally applied oscillatory force. Whoa, that one's much more complex, much more full in it. Okay, now we need we need a Britannica whisperer. What do I mean by that? It turns out this is very densely based information. This is Wikipedia. And what we get out of, for example, Copilot or Gemini or ChatGPT those things are more simple in their thing. It turns out it's not true. It's not just the natural frequency. Okay. Now, by the time, but before I get to this, I want to introduce you to an idea. Okay. And this idea, that means I need to switch over to a view on the tablet. So that's exactly what I'm going to do. Stop sharing this. Share from the tablet. Okay. Be prepared. We might be interrupted soon. Okay. Here we go. Let's bring it up again. All right. Now let me go find our tablet pen. Okay. Now, the whole idea is that something that has simple harmonic motion will repeat itself more or less like a sinusoidally. Okay? Repetition, which is meaning like a sine wave. Okay? I'm putting wave in parentheses because it may not be a wave. It's, remember what we mean by sine wave is that because if we were to plot it in time, it changes position, it changes state, it changes its characteristic, whatever that characteristic is. Okay. Whatever that characteristic is. It might be a position, it might be an angle, it might be something else, but it changes something in time rhythmically. That's the whole idea. And it does this rhythmically over and over again the same way. But it turns out that things don't necessarily have to be rhythmic. Okay. So they could do this. Now, here's the x-axis, if you will. Okay. I didn't do it that way here, but it was implied. Okay. So now what I'm going to imagine is this. Suppose that I go up and then down and then do this and then up again, then go down and up again like that, and then up and down and then up again. What I'm trying to say is this. What if one part of this thing, oops, hold on a minute. What happened? I wanted, oh, really? I'm accidentally changing. Okay. There's something wrong with this thing. Okay, this is what I wanted. Okay, that's fine. And now change. What I'm trying to get it to do oh well, what can I do? Here we go. This is what I wanted. I wanted blue. Okay. All right, go back to this. Okay. Now, what I was trying to show is that this part here Okay. This part, this part repeats the same way. It has some characteristics. It takes more time to do it. It takes, but this part here takes less time. And it's just different somehow. Okay. Now, if you connect all these things together, what happens is this is not a sine wave. Okay. It's not a sine, it does not have sinusoidal character. It's sinusoidal in a way, it's rhythmic. Okay. It's sinus because it repeats over and over again, but it's not a sine wave. So the whole idea behind this is that, well, wait a minute, what does this mean? It means it has more complex motion to it. It has, and what happens is, if we were to listen to it, if it were a sound, we wouldn't hear a single tone. We might hear something that has more than one tone inside. Now, I'm going to introduce you to something that's actually quite advanced. Okay. This is taught always, to physics students. It's taught to engineering students. I don't know about computer science students, but it's so you'll find in physics, mechanical engineering, in civil engineering, in you need to know this also in metallurgy. Okay. Industrial engineering, a whole bunch of other stuff. Okay. Uh, and what we're talking about, this is a rather, we're not going to go through the mathematics of it, but I'm going to show it to you from the perspective of a, how should I say, a music head, a audio head, somebody who's really into audio, and has to have the best speakers. He's got to set up his room or where he listens to music in just the most absolute perfect way. You don't necessarily have to know mathematics for this thing, but you do have to understand the properties of sound and vibration in general to make sense of this. Okay? Now, it turns out that like I said, not everything is a rhythmic repeater of um, of motion. Even springs, for that matter. You know what? I'm wondering if I could show this to you. Let's see if I have this. Give me a moment. What I'm going to do is I'm going to go and look through my images for spring. Why am I spring? Give me a moment. I'm looking for images and dot JPEGs. I don't have it. Okay. What I want to show you is the motion of that I've observed with my phone on the spring. And what happens is sometimes it looks like this. Okay. It goes up, then down, and then it goes like that really quickly. And then this, and then you get this, and then like this, and then like this, and then this, and then like something like this. I'm making part of it up, by the way. Doesn't make any difference. You can see this if you do it this way. So let's take a look. Actually, let me show it to you real quick, see if I can actually get this thing to do it. So I'm going to use Physics Toolbox Suite, and I'm going to actually let's stop sharing so you can see what I'm doing. Okay, here's my spring. Here it goes. That's enough. Okay. Now let's pause it and let's show it to you on here. So what you see here is that it's not even near a perfect sine wave. It's not even near a perfect. Well, okay. Some people might think it looks like a sine wave, but like right here, or I should say right here. So it doesn't look like a sine wave. And that's where I started out. It doesn't always look like a sine wave. The point is that even when it's on the spring, it's not perfectly sinusoidal. It's not perfectly a sine wave, if you will. The word wave, remember, is we use the word wave, of course, as a as a descriptor, as a shortcut, to mean something else. Okay, it looks like a wave there. Okay, but it's not sine. It's not a sine function wave. Okay, now the thing about this is this. If you look at this and you ask yourself, how many different ways is it possible that we add a whole, let's share the tablet again, because I'm going to draw it out conceptually. Share, right? How many different ways, if we were to add in, wait a minute, what I want to do is I want to say, what if I can take this and then add this? Notice I changed the function. Doesn't make any difference. And then add in this. I'm just making this up as I go along. Okay. And then you add up some more and add up some more and add up some more. How many different things do I need so that it would look like this? Okay. It turns out that you get a whole bunch of things, sine waves together, that makes it look like this. So it turns out a lot of sounds actually sound like this. Now, what I'm going to do is I'm going to play several different sounds, okay? And I'm going to play those sounds on the phone. They were going to be picked up by, of course, they're going to be picked up by the microphones here. And then what I'm going to do is that in fact, I'm going to have the tablet also record it. Okay. And then what I'm going to do is I'm going to show you what those, when we do the sounds, okay, let's see, what the sounds actually sound like. Okay. So hold on, let me set this up because I need, once again, I need an app for my tablet, and I need an oscilloscope, a thing, OSC. Here's oscilloscope. Okay. All right. Oh no, I need another. Maybe it. Hold on a minute. Let's see if we can get another app going. Not that one. Um, Physics toolbox. Oh, all right, fine. Okay. Is there an oscilloscope? Yes, there is. Nice. Okay. No. All right. I have to download it. Let's see if we can get a better oscilloscope. Okay, search for an oscilloscope. I want it on my tablet so you can see it. Okay. All right. This one sounds okay. Give it a moment. It should be opening. These things are really short, often. Okay. Yeah, there we go. There we are. Okay. Yep, it works just fine. Now, with ads and everything. Great. Okay. Now I'm going to use an app that you may not have heard of before, but if you want to annoy people with it, it's a great app for annoying people. The app is called PA Tone. Okay. Here's, oh, sorry, it's backwards. You can see it at the top here. PA Tone, PA Tone Generator. Okay. And I'm going to set this up for 300 hertz. Okay. It's going to make a series of waves. Okay. And now what I'm going to do, you won't see this for a moment because what I'm going to do is I'm going to share the tablet. Okay. So let's share the tablet because you'll see just that. There we go. Let's expand this up. There we go. Sounds good to me. Of course, with the ads. All right. Now let's see what happens. Oh, sorry. 300 hertz. Okay. Sound on. Oh, maybe I have to drop this. All right. Oh my goodness. I don't know if you hear me or not. Okay. There's something went wrong with. Okay. We're going to stop here. And we're going to restart this because unfortunately there's something wrong with the audio. Okay. So what we're going to do is I'm going to stop share and then I'm going to stop and then we'll restart this. Okay. All right. And now.